Now I'm going to talk about accelerating knowledge transfer with open hardware. I'm going to give examples from my own lab, the Free Appropriate Sustainable Technology Lab, and the scientific community. And so this is how I run my lab. And it's very different than most of the other labs on campus. Everything, like the F in FAST, is free. Everything I do is free to everybody. You want to read my scientific papers? Everybody else's scientific papers are behind paywalls. Mine are free. You want to see my literature review so you know what I'm going to do next? That's up on the web already. The methods on how I've done every scientific experiment my entire life, except for when I was in grad school, are up on the web. The hardware designs, if you want to replicate what is in my lab today, you can get to all of them. The software source code and the firmware are all free, and we basically free everything else. So like the last book I published is free. You want to read about how to set up solar for yourself? You can download it and start reading it. And you might imagine how a dean would feel about somebody like this. So in the US, when you get a job as an academic, you sign away all your intellectual property rights. You say the university owns them, and maybe they'll give you back a couple pennies, if you patent something. And here you have a professor that's literally giving everything that he's done away. And I will admit, when I first started doing this, and I started it in the US, I was a little scared because I wasn't sure it was going to work. It represented a fairly large risk, but I saw what was going on in open source software. I was really frustrated with how the patent system was so slow. I wanted to be able to go faster. I wanted to be able to go as fast as Linux could. And so I decided to take a small risk, and I started making some of my stuff free. Then it started to work so well that I was like, why am I holding anything back? I might as well go fast on everything. I might as well put my foot on the accelerator. And so that's what I did. So why do I do it? Applying the open source methodologies of doing technical development is more effective and more productive. How do I know this? At a typical R1 research university in the US, somebody like me, an engineer, is expected to publish 2 papers per year. Here at Western, we're better than that. So we're a top 1% in the whole world type school. My colleagues across the street publish between 5 and 7 per year. My group publishes 40 to 50 papers a year or more. How is it possible that we do that? It has nothing to do with how smart I am. It's all about the methodology. Everybody over there that's smarter than I am could be doing way more than they are now simply by changing methods. Because we produce more, we're cited more, which makes it more likely that we're going to get grants, which makes our group size larger than everybody else's. So my group is one of the largest, if not the largest on campus. I have 35 HQP. When you see an HQP to a professor, that means it's at least $50,000 per year per PhD student. So my burn rate's around $1.5 million just to cover my people. They create technologies faster than everybody else. How? Not because they're necessarily super smart. Now, I do attract the smartest, and if any of you are interested in research afterwards, I'd be happy to talk to you. But the way that we get more productivity is that we have the entire global engineering open hardware ecosystem helping us. We get their help by sharing our technologies. The better they are, the more people want to help us, and then they do, and then we continue on. We have super easy collaboration. When I meet a new industry partner, I don't need to get the lawyers involved. I don't sign NDAs. I shake somebody's hand. I say, we're going to work with you. Everything I do is going to be yours, and you can use it. And that is fairly convincing to most companies, even some that aren't as familiar with open source to begin with. Because we're doing all this, we're generating so much more information. We get cited more, which gives us more exposure, which gives us better grant opportunities. We have no secrets. Everything, like if you want to walk over to my lab right now, take pictures of everything that we're doing, by all means, do it. We reduce costs. I'll show you some evidence that open source hardware radically decreases the cost of scientific equipment, and because my equipment costs are lower, I can then afford to hire more people or buy more and fancier equipment. And then finally, last but not least, because all of our stuff is open and we have such a large footprint, we're so visible, I get the best students, and I get the best work from those students, because instead of working on some sort of proprietary little project in the corner of the lab that we can't let anyone see, our stuff is way out in the front. It's on the news. And because the students put their names on everything, they're in the news. They want to have their best foot forward. Everything we do is open, and so you can't hide behind bad work. And so I get the best from my students as well. So as a general rule, when we're talking about open source, it's all founded on the principles in open source software. And so what does that mean? That means that if you write a program, you write an app, you make it available in source code form so that people can actually see how it's made. And then you give them a license that lets them do pretty much anything they want with it. They can copy it, they can use it, they can study it, change it, improve upon the design. But it always has this viral component to it, which says that if you make the software better, you have to reshare it with the same license. That concept in software is ported over to hardware. So the same ideas, you can do anything you want with the hardware, you can even sell it, but if you make an improvement, you got to reshare with the whole global community with the same license. Now, what does that lead to? Well, that viral component where everybody that looks at the software or the hardware and makes an improvement immediately reshares it, you get faster innovation. Because then it's just not your tiny little company. It's everybody's company. It's all the hacking academics out there. There's a bunch of people in their dorm rooms or their garages making technology better. That faster innovation gets to superior technology, and it allows everybody to value harvest from it. And I don't want you to think for a second this is anti-business. This is like super pro-business. If you look at what has happened in our world, like the internet age, the thing that you're all familiar with, all of that is run on open source software. Basically, all the servers of the world are running open source software. All the supercomputers, every single one, including the one on campus, is running open source software. Why? Because it's better. It got better because more people worked on it. IoT is also dominated by open source software. The AI revolution that you're hearing about, you know where all that software is written in? Open source. And there's good examples, like Red Hat was sold to IBM for $34 billion. This is a company whose main product was free. You could download their version of Linux, run it on your laptop anytime you wanted for free. You could burn DVDs and sell it on street corners for free. Yet they somehow were making billions of dollars a year. And that's because they figured out how to get a profitable open source business model to work, where they took something that was pretty good, made it even better, and then reaped enormous profits from it. Now, even in the days when open source software was kind of taking over, the software advocates didn't think hardware would work. And the reason they didn't think it would work is because software, if I make a program, I can email it to you. It basically costs me nothing to send it to you, and you can run it. But in hardware, if I do a design and I email it to you, you still have to make the thing. And that is made out of matter, and matter costs money, and it's hard, and needs energy, and there's no obvious way to do it. Then this RepRap project came along, and the guy on the left is a professor at Bath University, and he was really into rapid prototyping. And he had this idea that he would use a rapid prototyper to make another one. And this was just about at the time when Stratasys, which is a big American 3D printing firm, their core patent on extruded plastic was about to run out. And so he had, at Bath University, he had access to one of these big rapid prototypers, and they would usually cost $500,000 to $1 million. Only a few universities like GM and Ford each had one. Like, this was not a common thing. So he used this super expensive tool to print out a bunch of little 3D printed plastic parts. You can see it there. I mean, that thing is a monstrosity, but it worked. He was able to make another one with the first one. He posted the designs online with an open source license, and then it went totally berserk. Hundreds of companies, thousands of people started hacking away at this, and it got quite good. And so one of the people that was hacking away on this was me. And the reason I came about this, you guys all know I'm a solar cell guy. I was working with MIT. They had this one laptop per child, a little green laptop on the left. And at the time, it was a $100 laptop, and that was so cool. Now it doesn't make that big of a deal, but at the time, our dream was to put a laptop in the hands of every child on the planet. We would have open source software, free educational tools. It was going to be awesome. And so we got this laptop. We pushed the price down. It was working great. And then they started to try to deploy it, and places they wanted to deploy it, the people that needed the education the most, of course, didn't have electricity. It's like, shoot. And so my job was to come up with a way to solar power it. So we made this clever little circuit, made a bunch of little cells, and our idea was we would put a piece of plastic to hold it all on the back of the laptop so it would kind of charge itself. You can't really get a solar-powered laptop on the market here, but there's markets overseas for it. So I finally I was at Queen's University. I was at a university with one of these rapid prototypers. And I was so excited, like any engineer. I think there's a couple of you in the audience. You know what this is like, where you could finally make your dreams reality. So we're so excited. We got this thing printed, and it was $65. I was like, no one could possibly do this. Like, it's almost as expensive as a stupid computer, let alone like way more expensive than solar cells. So I was searching on the internet. There's got to be a better way to do this. And the RepRap project came up. And I got to tell you right then and there, I salivated because I knew this was going to be freaking huge. So I immediately bought one, and that's the one in the upper left there, and it broke the very first time I built it. So it took me 2 students an entire summer to put it together. It broke on the first print, and the poor student had to hold the corner together as we printed out another corner. That thing was a piece of garbage. Both of those students quit in frustration. Second semester, right after that summer, that's Brennan over there on the right. That one only took me 1 student 1 semester to build. And you can notice that it still looks like a bit of a monstrosity, but it's getting better. And at the time, I wanted to use it for real things. Like, I wanted to print actual products from it, not just use it as a toy for like a gimmick to look at. And so I was posting on the web, and people were fighting me and saying that, these 3D printed things are just garbage. Like, you could just look at stuff. You can't use it to do anything. So my experience said that that was wrong, but I needed a way to prove it. And I didn't have any money for this, right? Because I'm a solar cell scientist. Very hard to switch fields. And so I used the open source community. So I posted on the web. I said, I will test your 3D printed parts for free. This is how you do the test structure. This is how the paperwork that you need to fill out, and you need to mail it to me. Hundreds of people all over the world, random humans in their basements, their garages, hacking away in the middle of nowhere, sent me samples. We tested them all. And those are the 2 graphs on the right. Now, the exact technical things you don't need to know, other than on the y-axis means the higher it up it is, the stronger it is. And that black line on the first one for ABS was Stratasys. So this is a top tech firm that had a 20-year head start against a bunch of amateurs in their basements hacking together things from junk. Most of us beat them. And the beautiful part about that particular paper is I had all the actual inputs that you needed for your 3D printer to beat them. So, of course, I published them. That's one of my most cited pieces of work. Why? Because it's super useful. Everybody around the world can use it to beat them. The other thing that's interesting is PLA. The open source community gravitated to that plastic polylactic acid because it's easier to print with. They weren't good yet. We didn't know what we were doing, so we chose plastic. It just turns out to be stronger. And so that particular paper shows how, with a bunch of random people on the internet, you can destroy a large company on a technical spec. Since then, things started to get really interesting. That leads down to that bottom project. And this is kind of what really pulled me into the field. I'm a solar cell scientist. One of the things we do, we shine light at solar cells, and we change the color of the light, and we change the intensity of light with a filter wheel changer. We use a filter wheel changer because we could use a graduate student to do this, but that's a very boring job, and no one would want to do that ever. So we have this little automated thing that just turns around and changes the filter. Mine broke. It was right at the beginning of the summer, which is when we get most of our research done. It was $2,500 to replace it, which is irritating, but not the end of the world. But it was a 5-month lead time, which means I was going to lose the entire summer for research. I couldn't do anything until I got this thing fixed. So I did something abnormal. I knew the 3D printers were just about there. We already used Arduino open source electronics to run some of our equipment. I hired a high school student to build me a filter wheel changer. And what he did is down there on the bottom left. I gave him a crappy computer from IT because I didn't have money for a new one. It couldn't run Windows anymore. It was so old. But I put on Linux. It ran faster. And then I put on OpenSCAD, which is just a script-based CAD package. The student picked it up in a week and was able to make the best filter wheel changer in the world in another week and print it out on that 3D printer, which again is made from mostly garbage. You can see like the power supplies from one of the other computers we just ripped out of. I could make a better scientific tool, exactly what I wanted, and make it parametric and share it with the whole rest of the world. So I did that in an article in Science. Science is one of the top or the top scientific articles at the time. And I was like, hey, everybody, look at what you can do. All you need access to is some of these open source tools, and you're off to the races. So that led me down to a very different area of research than I ever thought I would get to. I started a 3D printing course. After the first year, it was sold out every year as soon as I posted it online, where 100 students would all have the option to build a 3D printer from scratch. And you'll notice that these 3D printers don't look anything like the previous ones. Why? Because somebody in Germany found that a pick-and-place robot could also be used as a 3D printer. It uses less parts, can be built faster, and all of those ones were built in under 8 hours by one person. So we went from 2 people an entire summer to 1 person in a Saturday afternoon. And these printers are technically better in every way. They're faster, they print better. Like, we started to add features to them. That was what all the graduate students that took the course had to do. And we got to the point where you could really start to use these as scientific tools. For the graduate students, I also forced them to make it better, make some sort of serious material improvement. So one of the first ones we obviously did was to make it solar powered. So now if you could get a duffel bag anywhere in the world, if you could use that as your check-in and your luggage, you had a mobile manufacturing plant that you could actually use. And so we actually started doing this. So this has been Out of all of my students ever, he's definitely the most adventuresome. He went to South Sudan during the war to work for Field Ready. Field Ready's claim to fame is they use open source designs to 3D print things that people need in disasters. So like there's a hurricane or a flood, they go in, use 3D printers to make whatever's necessary there. They use 3D printers that are ruggedized to be used kind of anywhere in the world. Now he is the CTO of Kigenzi, which is a Kenyan startup that does open source 3D medical printing. So they work for hospitals, they make tools that aren't available there, and that little clubfoot brace is a good example. So this is a better clubfoot brace than you can find anywhere on the market. It's very easily customized. It's manufactured anywhere you can get a 3D printer, and it costs less than all of the current methods of doing it. And so you can get better equipment, you can even get it in the hospitals, and you can do it for far, far, far less money. If you could 3D print in plastic, you can also start to 3D print in other materials. So we've done steel with the heads, like just using a MIG welder. We've done ceramics by putting on a syringe pump. You can put on a milling head, so you can do PCBs. For the electrical engineers in here, you can probably tell the difference between the professional one and mine. But it doesn't matter because they both work. So yes, the professional one is slightly better. Not quite as much vibrations, but only so ever slightly. So the model for open source hardware for scientists is this. You have the first scientist that needs something for herself. So she designs some sort of special test tube. She takes a very modest additional effort and posts it on the web with an open source license. Then you let it sit and see what happens. Maybe a couple months later, somebody takes that test tube and makes a test tube stand. Somebody else makes a centrifuge from it. And because everything was licensed open source, they had to reshare them on the web. And so then the first scientist, taking no extra effort whatsoever, now can have herself a test tube holder and a centrifuge, basically for the cost of materials and a couple pennies for electricity. So this kind of stuff actually happens all the time. This is a bunch of things that my lab did for chemical mixing, where we're taking the place, so say the middle one, that is a $50 version of a $2,000 device that just spins bottles around so you can do bacterial cultures. We can do massively expensive things for almost no money using this replication process. Now, open source hardware is roughly 15 years behind open source software. This is a graph of the Google Scholar citations as a function of year for software and hardware. And you can see, software has been around for a little while, since like the 90s. A couple people noticed it. But hardware really didn't get started until the early 2000s. And then it took off. So these are all exponential curves. They're growing extremely quickly. Why is it growing in the scientific community? Because of the price savings. We did a review of all of the open hardware published in the literature, and the average savings for the scientist was 87%. If it had an Arduino in it, so an open source microcontroller, and uses 3D printing, that number jumped up to 94%. So to give a feel for what this means, one of the things my group did early on was a syringe pump, and we needed it for our own research. But then people started using it for all kinds of things. They used it for electrospinning, they used it for biology, they used it as a fluid handler, for a robot. Then it made the cover of 3D printing and additive manufacturing, because once you had control of the syringe pump, you could mount it to a 3D printer, and you could start to mix materials. So usually you extrude or you do like an SLA process. With this, you could do both. And that means you could get any material you want, no matter what it is, in a photopolymer to print in any shape. Then they got even better and put some force feedback on it, so now you can actually use it as a scientific tool in and of itself. So if we look at this from the perspective of a scientific funder, if the NSF or NSERC is going to give me money to do something, why would they do that if I'm just going to give it away for free? Well, it turns out that these are extremely valuable things to do for scientists. Why? If we just use the syringe pump as an example, the cheapest one you can find on the market is from China. It's really junky and rickety, probably won't last more than a week. It costs $150. The good ones, like a dual syringe pump like this, cost over $2,000. And the first month that I posted these designs online, they've been downloaded more than 1,000 times. So the downloaded substitution value, the value that was created from those designs being downloaded and manufactured, was between 168,000 and 2.5 million. And since then, it's been downloaded so many times, it's well over 20 million. Like, I can say that with conservatism. I know how much it cost to do this because I was the one who did it. So it cost about $30,000 in labor, and I had a 52% overhead at the time. And that means the return on investment for the scientific funders that funded me was 750% to over 12,000%. Those are the kind of numbers that get most people at least sitting up in their seats and paying attention. It has enormous possible scientific impact because so many people could use it throughout the world. Other examples are open source optics. The savings are between 97 and 99%. Really good example is optical rails cost $380 a meter. Open beam costs $12 a meter. Does the exact same thing, can be used in exactly the same way. To give you a feel for how powerful this can be and how you really utilize the international open source engineering collective, I had another scientific problem. I needed a lab jack to move something in the way of a light beam and out of the way. That's almost all the things that I do. Got a quote from the company that gave me the original tool. It was almost $1,000. Now, this is a lab jack. This is the same thing as the lab, like the car jack that you have in your car. It's only weaker and it doesn't do anything. It's not automated. You turn a little crank, it goes up and down. So again, I hired a high school student. I was like, this is your challenge. Build this for me by the end of the week. He did, and that's the black one in the back. He posted online, and somebody in Poland that we don't know was like, hey, you guys put some of your pieces together backwards. Try this, and you'll get larger extension. We turned it around. He was totally right. We fixed our system for us. A couple months later, somebody in France saw our design and made a better one, and that one uses far less fasteners. It's mostly 3D printed. And then a year later, somebody in Seattle made one that was 100% 3D printable that you could just print using no fasteners. So it's the cheapest solution, it's the best solution, and this is the solution we now use. You could also start to go after higher end things. So if you're going to do semiconductor research like me and try to make really cheap solar cells, you need to be able to lay down very thin layers of semiconductor material, and it needs to be uniform and over large areas. And so one of the ways you can do this is with a slot die system. And when you're testing new slot die systems, you go to a very high-end machine shop, and because you can see kind of like what they look like on the inside. So they have to machine out the inside. That's very challenging to do, very expensive. And for a little tiny one like that, it's $4,000 per slot die. Now realize the geometry changes the type of fluid flow that you have, so you might need to do 10 of them before you get the right answer. We found that we could 3D print them. And so we have a little bucket in our lab that has a whole big bunch of failures, but each one of those failures only costs about $0.25 to print. And so we were able to get down to 17 nanometers thin films using an old 3D printer that was no longer good for plastic 3D printing anymore, and a 25-cent piece of plastic. So these types of innovations started to really catch on because now everybody else could copy what we're doing to make the thin films, and they started to do it. Now, once you make those thin films, you need to test them. And the way that you would do this in industry, like let's say you're working at Intel, you would have a $250,000 mapping 4-point probe system that kind of like is a little robot that takes a 4-point probe and bounces it around your surface. Well, no one has these. In fact, you can't even buy them. This is like a special custom thing that Intel and a couple other big manufacturers would have. So we took an old 3D printer. This is actually one of the Lowell spots. This is, I want to say, number 68. And so Lowell spot was going through the innovations cycle so fast, their printers, like every generation, got better than the next one, so much more that you'd feel almost bad using the old ones. And so what do you do with the old ones? Well, you could use them. And so we took a $4,000 print head, we did our own electronics and open source software based off of a code bank of other people, and made ourselves a mapping 4-point probe. And what's better than that, because it already had the heated bed of the 3D printer, it was the first, as far as I know, heated mapping 4-point probe system that we built for, let's say, $5,000 and replaced a tool that would cost at least $250,000. And I know $250,000 doesn't sound like a lot now, but at the time that was like a house. So you can have a house or you can have this tool. All right, so when I talk to scientific funders, this is the spiel I give them. When you look at the conventional way that we fund scientific hardware, it's like the system on the left. At the NSF or the NIH, which are the two biggest funders in the US, your chance of success for writing a grant is 7%. And that's pretty dismal, and it's depressing, and it's kind of the worst part about being a scientist. And so when somebody spends hours, it usually takes about a month to write a proposal, they spend a month of their life writing a proposal, and they send it in to the NSF, they know almost certainly they're going to lose. And you look at that little cartoon, and you see a bunch of unhappy scientists. 90% of the scientists are unhappy, only one person gets the grant. And you notice that person has white hair. Why? Because the people that are going to get the grants are the ones that have already demonstrated that they're good at it. They have to be old, they have to be established. They're not going to take any kind of person just got their PhD. We use the open source model where instead of funding the purchase of a proprietary tool or the development of a proprietary tool, you fund the development of an open source tool. Now, the first year, everything looks the same. You still go to the high-end scientist with the white hair. Everybody else is still unhappy. But where things change is in future years. Because in the proprietary model, every year going into the future, you still only get one of your scientists being happy. In the FOSH model, because it's 10% of the cost, that second year, because of the development, you can fund everybody. Everybody gets the tool. And it's not just last year's tool. You fund them to improve it. And because it's open source, everybody gets the improvements. And so you track this out to the 10th year and add everything all up. In the proprietary model of funding scientific hardware, 90% of your scientists remain unfunded, and the majority of the ones even that you funded have equipment that's no longer relevant. It's old. So you think about your cell phone 10 years ago. Like that's not, probably doesn't even do anything that you could do now. It's a piece of junk. Same thing is true of scientific hardware. And so the open source hardware model gets you the majority of your scientists, 91% funded, and they're all funded with the state-of-the-art equipment that they can continue to use indefinitely. So everything I talked about up to this point was what I'll call lateral scaling. And what that means is that me as a scientist shares a piece of open source hardware. Another scientist somewhere else in the world takes it and does something with it. Maybe they share something back with me, maybe they don't, but we're on the same plane. I'm not selling anything to them, they're not selling anything to me. And you might say, well, that's still good for science. That makes some sense. And maybe as a business, when I leave here, whatever company I end up working for, I might use that method. I could team up with universities, they can move faster. And if you're doing that in Canada, the MyTax or the NSERC Alliance grants, the way you would do it. If you're doing it in the US, it's the SBI or STTR methods of funding. But most of you are probably not going to do that. And that's why I want to talk about how you make money from this. So even in this very narrow area of scientific tools, there's a huge amount of money to make. How do I know this? Because of the emails that I get. I thought, I would say almost naively, that if I made a cool scientific tool, posted it on the web, my job was done. I could tap out, they could download it if they wanted or not. It didn't really matter to me. And if I got something back from it, great. And what I've learned is that I get a huge amount of stuff back, but also that doesn't fulfill the need. I get all these emails to like, please, can I buy your syringe pump or can I buy X device from you? I don't want to sell it to them. I'm a university professor. I got enough things going on. And sometimes my students spin off companies. But the ideal case would be where you're providing what every customer needs. And every scientific customer, just like every normal customer, is going to be a little bit different. And so there's a lot of business opportunities to fulfill them. And so I want to talk about a bunch of business models you could use that we've applied or seen applied to the scientific field that could be applied to any field. And so the first and the easiest, if you want to start a hardware company tonight, you could do it with kit supplies. Why? Because there's low overhead and extremely low risk, and you avoid most regulations. So let's say this open QCM or quartz crystal monitor is a way to measure extremely tiny things like the mass of a gas. And for people like me working on semiconductors, I could use something like this, but I might not necessarily want to build it from their plans, or even if I do build it from their plans, I need to buy a bunch of really special components. It gets super expensive. Wouldn't it be nice if somebody made a company that sold me a kit and I could put it together myself? Well, look, they did that. They make serious money selling kits to people like me that want this tool. You could also start to sell to scientists that are makers in other things. So OpenBeam is a good example from that. It's an aluminum extrusion that fits M3 nuts and bolts. It's very slick. It's good enough that you can use it for optical rails, but you can also use it to, say, build robots or build different types of equipment that you want. And so they're selling something to the community of people that are makers. They're making one thing and they're doing it well. Shapeways is an example of providing printing services to people that don't have them. So at Western, we've got, I don't know, a couple hundred 3D printers probably, but we only have a couple that can do specialty materials or metals. And so if I want something out of a very fancy material, I can go to Shapeways, they'll print it for me, they'll take a profit of it, even if that design is open source, like this Dremel which was developed by an Irish grad student to turn a Dremel drill into a centrifuge. Normal scientific suppliers can also make money even if open source products are starting to eat away their kind of core products. And they can do it with calibration and validation services. So if you make a new spectrometer, you can go to somebody like Ocean Optics to calibrate it for you. You pay money for that, but then you have a less expensive spectrometer and you know it's just as good as the conventional ones. You can also just sell open hardware. And this is maybe the most obvious business model where you make something, you sell it for more than you made it, you get profit. So OpenPCR does this, Backyard Brains does this, SparkFun does this. And for all of these, they're selling to the scientific markets, but they also have larger markets. SparkFun in particular is selling to like the entire electronics industry and electronic copyist industry at the same time. One of my favorite models is you sell tools to make more tools. And so you could be somebody like Lowellsbot that sells 3D printers, but they also sell specialty things specifically for scientists. So they sell a bioprinter for about $10,000. Now, in the low-end 3D printing market, that's a really expensive printer. In the bioprinting market, that's a really inexpensive printer. Like they completely undercut the kind of conventional proprietary bioprinters. The system does everything you want to do, and it comes with software that's, again, open source, easily to adapt, and you can hack the machine to do other things for yourself if you're interested in it. You can resell other people's open source hardware. So MatterHackers does that for 3D printing. There's a whole big bunch of Arduino distributors, both from big all the way up to DigiKey, which is like a giant company. This is probably the model. This is the one that I use the most for open hardware companies, and probably most of you will find the most useful because you're probably going to end up at a major firm, and you might say, well, what does open source hardware do for us? And what it can do for you is expand your market. And so let me give this example of Superior Enzymes. So this was a company that sells enzymes. They manufacture enzymes. I don't even really know exactly what an enzyme is. I have nothing. Like I didn't take biology in college or in high school. What the heck am I doing working for this company? They came to me because I made an open source spectrometer that could do water testing. And one of their major markets was water testing for nitrates. And they saw this tool that was way less expensive than everything on the market. And they're like, holy crap, maybe we could use this with our device. And so we teamed up and they paid for us to develop that tool in the middle. And so this is a handheld device that works with any Android phone or device that is matched up specifically to their enzymes. So you buy enzyme kits from them. You can test water. You can test forage at the farm. You can use it in science classes. And so they went from a company that only sold things to like the EPA, like major environmental testing labs, to everybody. Because now you can make that little spectrometer for $50 if you're using my plans, or buy one for them from a little bit more. But you have to buy all this stuff on the right. And the stuff on the right is where they make the profit. And the stuff on the right is new products that they didn't have before because their spectrometers were too expensive to allow them to, for example, go into the high school market. And so now they can teach high school students how to search for nitrates and phosphates and look for pollution for almost no money. They sell more of their enzymes. They train the next kind of generation of scientists how to use their stuff, and they got it EPA approved. So now they're taking the place of extremely expensive lab equipment that you can literally do out in the field. And by you, I mean basically everybody. Like you don't need a PhD in water safety, whatever. You can just follow their simple instructions. Lots of people use this model. The people that make GPS chips provide open source drone plans. And you're like, why would they do that? So they can sell more GPS chips. This is a way you can tap into markets that don't exist yet by providing open source plans and kind of like feeding into the hacker community. And lots of companies have done this. Now, in a really unfortunately titled blog post, Elon Musk open sourced the patents for Tesla. And when it first happened, everybody just thought he was just bonkers crazy. Like, guy's a nutball. He just did something crazy again. What does that sentence even mean? But when you dig down into it, what was he trying to do? Well, he was trying to become a platform technology. And so in open hardware, one of the really popular platform technologies is Arduino. So you have a company, this little Italian company, and Italy is not known for manufacturing awesome electronics, made a really good microcontroller. It then started to show up, because they open sourced it, it started to show up in all different kinds of products. Now there's, I don't know, tens of thousands of products with these little Arduinos in them. They've made millions and millions of dollars. Why? Because they became a platform. So now picture yourself, let's say you're going to start an automotive firm that's going to do like one component that you add on to a car. Which company do you make your part for? Well, Tesla just said that if you don't directly compete against them, they're not going to sue you into oblivion and you can use all their patents. I'd probably aim it at a Tesla. And how do I know that this is what car companies would think? Because a couple months later, Ford did the exact same thing. So as crazy as Tesla is, Ford made the same announcement, joined a bunch of collectives to make both software and hardware for cars so that they would become the platform technology, not get eaten alive by Tesla. This kind of concept gets to the idea of a producer coalition. And the first one I ever did was actually for solar panels, where at the time the Green Energy Act had passed, solar was coming to Canada, or at least Ontario, in a serious way. And one of the first questions you talk to anybody on the street about is, well, what about the snow? Will that destroy your solar panels and they don't work in the snow? And so every solar company really in the world that wanted to sell in Canada was coming by my desk to ask about these snow studies. And so I did something similar where I said, well, we're going to share everything, but you got to give me everything for free. We'll give you your data back, but we're going to share everybody else's. And so we started to push out papers like these. And the good news is, in Ontario at the time, the snow losses were around 3%. And so it didn't affect the economics that much. Still made solar super economic. It was all great. And I could tell you, if you haven't noticed outside, those snow losses are almost certainly lower now, so it's becoming an even smaller factor. But how did we do all this stuff? Because remember, I'm a hardcore semiconductor guy, and that looks like a bunch of software. How did we do it? Open source software. We used open source computer vision and machine learning in order to be able to develop all those things. And then the guy there on the right is Rob Andrews. He was my first PhD student ever. He became a master at open source software. So what did he do when he left the university? He started a firm based on the fact that he was the best person in the world at the software, even though it was completely free. And that firm just got sold, I think it was 2 years ago, to a major player because they'd taken over the entire market. So what they were doing is monitoring large-scale solar farms, finding out when something wasn't working right, using an open source stack to be able to do it. And so what we're doing now up at the farm, and Next year, when you guys come back to visit your alma mater, you can go and take a look at it. We're building this big agrivoltaic test center using that same sort of methodology, where rather than wasting time writing grants, I use partnerships to get things done. But that doesn't mean that I can't pull in large money. As an example for this, we just won $1 million to build the first agrivoltaic agri-tunnel. So this is where we take that concept of agrivoltaics that you learned about before, but rather than shoot the electricity to the grid, we feed it into a tunnel that can be buried or not buried. But the idea is that it's used to power the grow lights and the pumps and the heat pumps that maintain the ecosystem for plants to grow. The density of food product that we can get from that is unheard of. And if this project works, and I know things are already growing there now, this is going to potentially revolutionize the way that we do food, particularly in northern climates. As our last example is support development of open hardware. And someone that does this very well is Seed Studio. So this is a company, they're making literally hundreds of millions of dollars a year on open hardware. And what they do is if you have an idea to make an electronic device, they bring it into their ecosystem, they manufacture it for you, they give you some of the profits back, and you make money and they make money. And so you can make more money by doing these partnership things. They're completely open about how it works. And if that is of interest to you, this is a way to get something off the ground immediately. So you can even take an open source hardware project that's developed by somebody else, maybe add a few bells and whistles to it, and then get it into an ecosystem where you can reach a global market immediately. So there is enormous potential here. Millions of open source hardware devices are already up on the web. They range from the very high-end scientific and medical tools to toys and things that you have in your kitchen, all different kinds of things, made of all different kinds of materials, smart stuff, dumb stuff. Everything that you could think of has already been made and be made open source, and you can make money from it. So I will talk about just a few more methods that scientists can use as a business model. One of these last ones is outsourcers. And so if I'm a scientist and I only have access to a finite amount of money, so I can't have every scientific tool that I want. And if I have a tool if I need a tool that I don't have, one of the places I can get that tool is Science Exchange. So I ask them for access to the tool, people bid on what they will provide it to me for, and then I get the science done by FedEx. I ship them samples and they ship back the answers. We already saw that open source scientific tools are much less expensive than the conventional variety. And so people that are contributing to the Science Exchange, because this isn't one company, this is more like a marketplace. So you have scientific labs from all over the place say, I have these services, and then scientists from all over the place buy those services. This is a way to have a competitive advantage because now you can have a lower cost because it costs you less to get started. And last but not least, we have selling open hardware as a service. And in software, this is by far the default standard way to do it. And we have Red Hat as the example of this, where they took something that was already good, tested the crap out of it, and then made it available to their customers, say banks, where they guarantee that it will work. And a bank that's going to lose millions of dollars a day if their servers go down need that kind of guarantee. And so you can provide that same kind of guarantee for hardware. You can provide support. One of the hardest things about running an open hardware company, or many companies, is dealing with the support. With people who are hacking around on your tool, can you provide technically competent staff to be able to help them go forward? People are willing to pay for that technical competence. Training, and this can be in all different kinds of forms, like magazines like Make Magazine, that's full of open hardware. What do? They sell a magazine. You could do web advertising like YouTube, or you could do workshops. Now, open source Ecology is a really good example for this. These people do large-scale open hardware, so like houses, brick presses, tractors. And the way their model works is they get money from both sides. So let's say you want a new house and you want it to be 100% green and completely open source and solar powered and whole 9 yards. They will come and build a house for you. So they'll ask you for some money to build a house and money for the supplies. And then they'll open it up as a training workshop. They'll have your neighbors come over to learn how to build a house. And in learning it, they will build a house. And so they get paid from both sides. The people that walk away from the training now know how to build their own house, or at least have some new skills. And the people that ask for the house to be built have a new house. You can also do consulting, and then you can do academic consulting or teaming up with people like me in order to try to drive the industry as fast as you possibly can forward. So I will stop here. I won't take any questions. We're going to switch right over to Alicia to talk about the Open Source Hardware Association, but we could talk questions at 3 o'clock. I wish you all the best of luck. Go make some money. There's lots and lots of money to be had. So thank you. Okay.